Okay, so what I want you to look at, eventually we're going to be on page 24 of your workbook, but there's a question up here that that's kind of leading into that. It says, for what angle theta does the sine of theta equal 1/2? And so my hope is that, okay, wow, sine of theta equals 1/2. I know this is one of my values. I could pick 30 degrees or pi over 6. I could pick 150 degrees or 5 pi over 6. And then, I mean, honestly, I could pick anything that was coterminal with that 30 degree or that 150 degree angle. So if I'm in degree mode, I could choose 30 degrees, I could choose 390 degrees, I could keep adding 360 degrees to that. Same thing with 150, I could add 360 to that to get 410 degrees. And I can just keep going either forward or backwards. Radian mode would work too. There's an infinite number of answers that would satisfy this equation. Or you could think there's two sets of infinite numbers that satisfy this equation. Okay, so what if we redefine how we're going to ask this so that there's exactly only one solution? And that's where we're going to introduce the inverse function. And there are two notations that you need to be aware of for inverse function. Our textbook uses this. Your graphing calculator uses this. You'll find out in class tomorrow. It's another reason why I want to invent my own calculator, because I don't like this at all, because it almost gives the connotation of a reciprocal, the -1 power. But this is not. It's referring to the inverse sine function. A better, more descriptive, I think, method is called arc sine. And in fact, we use this in calculus next year. So I'm going to use these both interchangeably. They mean find an angle whose sine ratio is 1/2. And so notice that it's already been solved for theta, and it's the inverse functions. Very similar but different to, it has the normal sine function. When it's the normal sine function or normal any trig function, there's going to be an infinite number of values that will satisfy that equation. If it's not that, if it's an inverse function, whether it's the inverse sine or arc sine, which mean the same thing, there's only one. And it's looking for the principal root, or the principal answer, or the principal solution. Now, I know that the principal solution is pi over 6, or 30 degrees. And we need to learn, where do those principal solutions live, in which quadrants? How do I make sure I get the right one? It's kind of similar to, just to make a quick analogy, it's kind of similar to the difference between x squared equaling 25 versus the equation x squared equals root 25. So both equations are very similar, but notice that this one does not contain a square root, and this one does. If the equation already has the square root, it wants the principal root, which in the square root, world, it's the positive one. If I have to introduce a square root to this, so I'm introducing a square root, then I need to think about that as the absolute value of x is equal to 5. And I actually get two answers. And so I want to compare that. If the inverse trig function's already there, it wants the principal root. Otherwise, if it's not there, if you would have to introduce it, then you get all possible solutions. Okay, so now we'll go to page 24. We need to be prepared to know, where do these inverse functions live? If I'm given a ratio, I need to sort of know a map of the unit circle of where I should draw these triangles, because it's going to be restricted. We don't want to have multiple answers when we're dealing with an inverse function. Remember last semester, we want it to be 1-to-1. We want one answer for every angle and one ratio for every, it's opposites. We have to restrict the domain. So if you would be given any positive ratio. So if it's arc sine, I'm going to use the arc one just to get used to that. Arc sine, if it's a positive ratio, you're going to put into quadrant 1. If it's a cosine, arc cosine of a positive ratio, you'll put it in quadrant 1. Arc tangent of a positive ratio, put it in quadrant 1. Arc cosecant of a positive ratio, arc secant my letters there, arc secant of a positive, and arc cotangent of a positive. So if you are given a ratio that's a positive value, all 6 of the trig functions as a positive ratio, you would draw then a triangle in quadrant 1, and only one. Now, if you are given a negative ratio, that's where we start splitting in terms of which quadrants you are going to put them in. If you are given arc cosine of a negative ratio, you're going to put into quadrant 2. Its reciprocal value, arc secant, will also go into quadrant 2. And then arc cotangent will be defined in quadrant 2. And we're going to look further in this tomorrow, but this is based on what does the graph of cotangent look like? Where is there a continuous piece of cotangent that I can put into an inverse trig function as a restricted value? The other 3 are going to exist down here in quadrant 4. So if you have a sine ratio, arc sine, that is negative, you'll put it down in quadrant 4. Its reciprocal function, arc cosecant, would be down in quadrant 4, as would arc tangent. And I should probably have gone back up to the quadrant 2 ones. If you think about, if you were to draw an angle into quadrant 2, and think about like what's negative over here as a reference angle, it's the x component. Your x value is negative. And notice cosine and secant depend on that x value being negative. So that makes sense to put cosine and secant into that quadrant because they're going to be negative in quadrant 2. And then cotangent depends on that negative x as well. It also depends on y. And so I could have picked either one, but the definition, I guess the standard definition of cotangent is when it's negative, you put it in quadrant number 2. Tangent depends on x and y too. So again, tangent could have gone up here, but the standard definition is you put it in quadrant 4, and again, it's based on its graph, which we'll look at again in class tomorrow. If you were to maybe draw in a triangle here in the unit circle and think about what about that triangle is negative, it's the y value. And the y value is negative, sine depends on that, and cosecant depends on that. So it makes sense to put the negative arc sine, arc cosecant in quadrant 4. Arc tangent, again, depends on both the x and the y, and in this case, it's the y that's going to make that down into quadrant 4. If you're a quadrant 1 and a quadrant 2 angle, so we're talking about cosine, secant, and tangent, cotangent, I should say, then you are in a smooth and connected value of 1 and 2. In other words, you're from 0 radians to pi radians, 0 degrees to 180 degrees. It's very continuous and connected in those 2 intervals. So I would think, that would be, so you're from 0 to 180 degrees. Those are going to be your range of values, and only in those 2 quadrants for cosine, secant, and cotangent. It's a little bit tricky at first if you look at the other 3 trig functions. If I'm sine, cosecant, tangent, you're in quadrants 1 and 4, but 1 and 4 aren't naturally connected if I start at 0, because I go 0 to 90, skip, 270 to 360. So instead, we're going to start down here and connect this way. And so the value down here is negative 90 degrees, or negative pi over 2, through 0 up to 90. So these answers would be from negative 90 degrees to positive 90 degrees. Or if you're in radian mode, negative pi over 2 to positive pi over 2. And again, we want to pick the 2 quadrants that are continuous, at least give you a range of angles that makes those continuous. Quadrant 1 and 2 is a little more natural. Now, look what's not, right? Nothing in quadrant 3. So that at no point when we're solving inverse functions should we be drawing in quadrants 3. Positives are in 1, the negatives split, and you have to know where those live. And I'll talk about that, like what's the geography of these angles. So a couple of examples that we'll go through. Follow along, please, on page 24. Maybe if I can, there it is, get my smartboard lined up. So the first one, very similar to what I started with, inverse sine of 1/2. So, I would draw this triangle, knowing that all positive ratios exist in quadrant 1. So 1 to 2. And I know if I complete this, that's a root 3. And I know that, oh, that's a 30-degree reference angle in quadrant 1. And there's no ambiguity because the inverse function's already been given to you. So it's 30 degrees, or if you want to leave in radians, you can say pi 6 radians. Okay? Here's our first negative. Inverse cosine is a negative root 3 over 2. And notice how I said this, inverse cosine. Don't say cosine to the negative 1, because that's not what this is. A negative 1 power would have meant do the reciprocal, which is secant. So arc cosine or inverse cosine of negative root 3 over 2. It's a negative cosine. It belongs in quadrant 2. That's where negative cosine ratios would be drawn. And so then we complete our triangle, negative root 3 to 2, 1. So this is another 30-degree reference angle in quadrant 2. So what I'm really looking for is, the angle that makes that. Remember, it has to be between 0 and 180. So if that's a 30-degree reference angle, we're talking 150 degrees, or 5 pi over 6. Okay. I might jump down to this one next, arctangent of negative 1 over root 3. So arctangent, it's negative. So I have to realize, if it's arctangent and it's negative, it's down in quadrant 4. So here's negative 1 to root 3, and there's 2. So we still have our 30-degree reference angle, but a 30-degree reference angle in quadrant 4 under the restricted domain of inverse tangent. Remember, inverse tangent has to go between negative 90 and positive 90. Even if there are other ways to represent that particular angle, in inverse tangent, if inverse tangent or arctangent is the given function, it has to give you a value between negative 90 and positive 90. So a 30-degree reference angle in quadrant 4 that fits that would be equal to negative 9 or negative 30 or negative pi over 6. And I like initially students that are like, well, wait, couldn't you choose this one? Because that tangent ratio is the same value. And yeah, the tangent ratio is the same, but I'm given inverse tangent. That has a restricted value of negative pi over 6. Okay? Inverse tangent of negative 1. So again, thinking about it, inverse sine of negative 1. Thinking that sine is negative, so I'm in quadrant number 4, and it's an opposite over hypotenuse ratio of 1 to 1. So that forces this to be 0, so that actually kind of collapses this triangle and puts us right here. It's one of our quadrantal values. So maybe some of you even recognize that as saying, it's down here at this coordinate 0, negative 1. And what value is that? Well, that's negative 90 degrees, because again, we have to be in that, like from negative 90 to positive 90, so that would equal negative pi over 2. All right, inverse cotangent of negative 1. Again, cotangent, now that's in quadrant number 2. So cotangent's defined in quadrant 2 when it's negative. And cotangent is adjacent over opposite, hypotenuse being root 2. And if you think about this reference angle, that's 45 degrees. But it's 45 degrees in quadrant 2, so the angle that I'm really interested in is the angle that gives us that value. So that would be 135 degrees, or 3 pi over 4. Arc secant 2, it's positive. All positive ratios exist in the first quadrant. So I don't have to worry about any other values, just first quadrant, 2, so 1, root 3. Secant, remember, hypotenuse over adjacent. So that angle is 60 degrees, or pi over 3 radians. We can come down to here, arc sine of 0. Maybe you recognize 0 as a value of sine, or if you recognize it as like opposite over hypotenuse is 0 to 1, there's 1. It's one of our impossible triangles. We actually are just sitting on the x-axis at the coordinate 1, 0. What angle is this? It's 0, or 0 degrees, 0 radians. Okay. Our cosecant of 1, again, that if you know the behavior of sine and cosecant, secant, and cosine, the 1s and 0s are usually they'll be the quadrantal angles. So if you forget that, you could always draw a triangle whose hypotenuse over opposite is a 1-to-1 ratio. Realize that's 0, and that means that our triangle is actually sitting up here at the top. That is equal to the coordinate 0, 1, and it's like that angle is 90 degrees, or pi over 2. Okay, part I and J, K, and L. You know, if you wanted to pause the video and try these 4, and then unpause it and see the explanation, see how you do, that'd be great. But we'll finish up with these 4 examples. Inverse cotangent, -√3. Quadrant number 2. -3 to 1 is my ratio. 2, that's a 30-degree reference angle in quadrant 2, but we want the obtuse angle, or the one that gets us at 30 degrees, which is 150, or I'll think of it in terms of radians, 5 pi over 6. Inverse tangent of -1, so inverse tangent lives in quadrant 4 when it's negative. It's a 1-to-1 ratio, and again, thinking about that 45-degree angle, but it has to be within -90 to +90, so we're talking -45 degrees, or -pi over 4. 2 to go, inverse secant. So this exists because it's inverse secant of a negative ratio. This exists in quadrant 2. So there's our inverse secant would be √2 to -1. Fill in that side of 1. So we have another 45-degree angle, but the value that gets us there is 135, or 3 pi over 4. And then our last one, inverse sine of -√2 over 2. And you know, you might start realizing and recognizing that these ratios we're seeing over and over and over again. So you might not even have to draw this. You might just see this in your head. You might see, oh, I know 45-degree angle has a √2 to 2 ratio for the sine, and so that 45 degrees sitting down in quadrant 4 as a negative value would have been -pi over 4. Okay, so hopefully that gets you a good base of where do the angles live. You know, that's the key to solving these, because you're going to recognize the ratios. Here's where they live. If you have inverse trig functions, there's only one answer, and you have to know exactly where that answer is in the correct representation. Is it 0 to 180, or is it -90 to +90? Okay, excellent.